two previous videos, you have been introduced with chemical equilibrium. Okay, in the second video, we already discussed on how to use the equilibrium constant. Okay, so we already discussed on how to calculate equilibrium constant and how to use ice table to solve problems involving equilibrium constant in both terms of concentration and partial pressure. Okay, so in this video, special for this one, I'm going to discuss and show you on how we can determine in which direction does the equilibrium going to proceed. Okay, because not every systems in this world are already established an equilibrium. Okay, so from the given concentration or partial pressure, you can calculate reaction quotient, which is in the terms of Q, and then we're going to compare the value of Q with equilibrium constant K to find out in which direction does the equilibrium will proceed. Okay, so we're going to go in more details about this in this entire video. Alright, so direction of the reaction can be determined by comparing the equilibrium constant with the value of reaction quotient. So just like equilibrium constant we have in the terms of concentration and partial pressure, reaction quotient Q also can be written down in the terms of concentration and partial pressure. Okay, if the reaction is already established an equilibrium, the value of K will be equivalent to Q. Okay, so how to write down the expression for Q? So expression for Q is exactly the same like you are writing down the expression for your equilibrium constant. Okay, so the rules that you always need to remember when writing down expression for both Q and K is we always remove the pure liquid and pure solid substance from our expression because their concentration remain constant over time. So we just included gaseous component or aqueous component in our Q and K expression. Okay, so the value of Q going to be varies depending on the given concentration and partial pressure for each compound, but the value of K going to be remaining constant unless there is a change in temperature, which we will discuss further in the Le Chatelier's principle later on. Alright, okay, so this is an example. Okay, so you are given A and B as the reactants and C and D as the products. Okay, so when you are, as you can see in the screen, the expression for both K and Q are similar, are the same, exactly the same. It just one is for equilibrium, whereas Q at any instant. Okay, not necessarily be in the equilibrium reaction, equilibrium systems or equilibrium moment. Q can be applied at any moments as whenever the reaction has been proceed. Okay, right, so there are three different Q value that you're going to compare with your K. So the first one, when your Q is less than your K. Okay, so when Q is less than K, the system has not yet established an equilibrium, and at this moment, okay, so you're going to have your concentration of products, okay, to be less than your concentration of your reactants. Or, okay, so the pressure of products is less than the pressure of your reactants. Okay, since we have more reactants, okay, so if we draw a seesaw, okay, so your reactant will be the heavier side and your product to be on the light side. Okay, so we want to reach an equilibrium where at both sides, okay, both reactants and both sides have the same weight. Okay, so what will happen? We're going to put more weight on the product side. So that's why the equilibrium, okay, the reaction will proceed from left to right. Okay, until your Q equals to K and equilibrium is already established. Okay, so secondly, when you're having your Q greater than K, That means your reactants concentration, product concentration is greater than your reactants concentration. That means if we draw a seesaw, your seesaw will be slanting towards your product. So your product has the heavier side and your reactant is on the light side. So to establish an equilibrium, that means both sides need to be similar in weight. So you're going to add more reactants. So the directions of reaction will proceed from right to left, R for right and L to left, until your Q equals to K. And lastly, when your Q equals to K, that means the system is at equilibrium, so no net change. Just a little reminder to every one of you. When the system's already established an equilibrium, it does not mean the reaction has stopped. The reaction still proceeds, but in the same rate for both forward and reverse direction. So let's apply what we already learned before about comparing Q versus K into this first question. So you're given a chemical equilibrium between NO reacting with Cl2 to produce NOCl. And in these questions, they already give you what is the Kc value at the set temperature. And they also give you what is the initial moles for every gaseous component that is present. So in order to calculate QC, that means you need to calculate the initial concentrations for every gaseous component that is present. So let's do that one first. So for your NO concentration, it is, the moles given is 2.0 times 10 minus 2 mole, and divide with the volume of the flask, which is 2 liters. And you will get it to be 1.0 times 10 to the power of negative 2 molar. So your Cl2, which is 8.3 times 10 minus 3 mole. Again, divide by 2 liters. So you will get the concentration of chlorine that is present at the moment is 4.15 times 10 minus 3 molar. For your NOCl, which it have 6.8 moles. So again, divide by 2 liters and you will get 3.4 molar. So your QC expression is exactly the same like your Kc, in which, since we are supposed to determine in which direction going to proceed, so we're just going to assume your reaction is proceeding from left to right. So NOCl concentration square, because we have 2 in the front of NOCl, and then NO square again, and Cl2 just 1. Then we're going to substitute with the calculated concentration that we did before together. So just substitute simply without adding the unit. So if you press your calculator, you will get your QC to be 2.786 times 10 to the power of 7. So I prefer if you leave out your QC or QP answers in the scientific form. That means simplify it to get the scientific form. So your QC is 10 to the power of 7, whereas your Kc is 10 to the power of 4. That means our QC is greater than our Kc, means we have more products compared to your reactants. So if we draw a seesaw, you will see your seesaw slanting towards your product because it is heavier and your reactant is lighter. So in order to achieve or establish an equilibrium, we need to add more reactants, so that it will become equivalent in size. So both reactants and product has the same weight and your seesaw become balanced. So in order to get that, to achieve that equilibrium, so the heavier part will be shifting to the lighter part, Or in other words, we're going to use up the heavier part, which is your product, to produce more towards the light part, which is your reactant. So reaction will proceed from right to left. Okay, so reaction will proceed from right to left until Q equals to K, where an equilibrium has already established. So this is the standard answer that you need to write down whenever you were asked to predict the directions of equilibrium. You were given the Kc value to be 65.0 for the following reaction, which is your hydrogen iodide decomposed to form hydrogen and iodine gas. Okay, so the following concentrations were detected in the mixture, and the question asks either the system is already at equilibrium, and if not, which direction must be the reaction proceed for equilibrium to be established. Okay, for this one, it's already give you the concentration, so we didn't have to calculate it again. So that means we just need to write down the QC expression first. Okay, so this time H2 is our product and I2 as well. And again, please make sure your equation is already balanced before you writing down your QC or KC and so on. Okay, so just substitute with the given concentration, 2.80, okay, 3.40, and your HI to be 0.500 square. So if you press your calculator, you will get your QC to be 38.08. Okay, so your KC is 65.0, whereas your QC is 38.08. That means your QC is less than your KC. That means our product's concentration, okay, is less than our reactant's concentration. It means we have more reactants. Okay, so if we draw the seesaw, okay, it's wrong. Okay, so if you draw your seesaw, you will have the reactant to be in the heavier side and the product on the lighter sides. Okay, so to achieve equilibrium, which means both sides having the similar weight, okay, so we're going to add more product. So reaction will proceed from left to right. Okay, so reaction will proceed from left to right until Q equals to K and equilibrium has been achieved. Okay, so this one means not in equilibrium. Okay, easy, isn't it? Okay, so you just need to remember the different condition for your Q value. It can be greater than K, it can be less than K, and it can be equals to K. And from there, you compare in the terms of concentrations of your reactants versus your product. So which one is more and in which direction it should proceed. If we have more product, it means we're going to use up the product and shift to the reactant side. If we have more reactants, that means we're going to use up the reactants to produce more product until your Q equals to K. Okay, so let's try with this one. Okay, so in the question 3, alright, so instead of giving you K in the terms of concentration, now we counter with a different one, which is in the terms of partial pressure. Okay, so it states that we have 1 atm for each gaseous component in the container at a given temperature. So 1 atm, 1 atm, and 1 atm. Okay, so that means we're going to calculate your QP. Okay, so partial pressure of NO square time with partial pressure of Br2 over partial pressure of NOBr and square. Okay, then we're going to substitute with the partial pressure value given, which is 1 atm. Okay, you don't necessarily need to include the unit, over 1 square. So at the end, you will get your QP to be 1. Okay, So the given Kp is 60.6. Okay, that means your Qp is less than your Kp. Alright, so system is not yet at equilibrium. Okay, so which one is more? So when Qp is less than Kp or Q less than K, that means our partial pressure of your products is less than partial pressure of your reactants. That means we have more pressure on the reactant sides. Okay, so if we draw a seesaw, you will see it's slanting towards the reactants because high pressure at the reactant sides and low pressure at the product side. Okay, so in order to establish an equilibrium, both sides need to have the same pressure. Okay, so that means we're going to add more pressure on the light side. So the reaction will proceed from the heavier to the light side, which is from left to right. Okay, so write a statement about it. So reaction will proceed, okay, from left to right until Q equals to K and equilibrium has already achieved. Okay, so are you clear now? Okay, do you have any more questions so far? It's so simple, isn't it? Okay, so sometimes they just end up with that kind of questions, okay? But sometimes they might ask you for a further questions, okay? Which let's look at question 4. Instead of just asking you to predict the directions of equilibrium, now you're going to have further questions, okay? And to calculate something else. Okay, so question 4, you are being introduced with PCl5, okay, and PCl3 and chlorine. Alright, so first, in which direction will the reaction proceed? So as usual, you need to calculate first the concentration. So concentration of PCl5, 0.1050 mole divided by the volume of the flask, which is 0.500 liter. Okay, so if you press your calculator, you will get it to be 0.21 molar. Okay, and for your PCl3, it's 0.0450 mole, okay, divided by 0.500 liter. So you will get the concentration to be 0.09, as well as for your Cl2, which have the same mole. So that means it's going to have the same concentration exactly like your PCl3, which is 0.09 molar. Okay, after calculating the concentration, now you can calculate your QC. Okay, so QC, so PCl3 concentration, Cl2 concentration over PCl5. Okay, then substitute with the calculated value of the concentration, 0.09 times with 0.09 over 0.21 molar. Okay, so you don't have to include the unit since our Q and K value does not have unit in our syllabus. Okay, so if you press your calculator, you will get your Q to be 3.86 times 10 minus 2. Okay, so the given Kc is 4.2 times 10 minus 2, just slightly smaller for your Qc. So your Qc is less than your Kc. Okay, so that means your product's concentration is less than your reactants concentration. That means we have more reactants. Okay, so if we draw a seesaw, the seesaw will be slanting towards the reactant because it is heavier and product is lighter. Okay, so in order to establish an equilibrium, again, we need to make sure both reactants and product concentration are about the similar size. Okay, so the heavier side will be used up and the lighter side will be more production. Okay, so it will shift from the heavier to the light side, which means in this case from the reactants to product, which is from left to right. Okay, so the reaction we'll proceed from left to right, okay, until QC equals to KC and equilibrium has established. Okay, so that is the formal answer, and you need to write down exactly the same like that, okay, depending on the situation. Okay, so next question, B, okay, so you given the concentration of PCl5 at equilibrium, and you need to find out what are the other components equilibrium concentration, okay. So now we need to plot an ice table, okay. Since it proceeds from left to right, okay, so your ice table will look like this. So PCl5, PCl3 plus Cl2. So concentration initial, so rewrite again what is the initial concentration, which is 0.21 molar. Okay, so your for PCl3 is 0.09 molar. It's the same with your Cl2, 0.09 molar. Okay. Right. After initial, your ice table should include changes in molar again. So PCl5 is being used up, so minus X. PCl3 is being produced, positive X and positive X. Okay, so positive 1X because we only have one stoichiometric coefficient for all of the gases component present here. Okay, so then to complete your ice table, we need to find out what is the equilibrium concentration in molar, and equilibrium concentration is simply initial plus changes. So 0.21 minus X, 0.09 plus X, okay, and 0.09 plus X. Okay, so given that equilibrium concentration for your PCl5, okay, is equals to 0.2065 molar. Okay, and from the ice table, the PCl5 equilibrium concentration is 0.21 minus X, so 0.2065. So you have to calculate what is the X value, okay, which is 3.5 times 10 minus 3 molar. Okay, and from that calculated X value, you can now determine what is the equilibrium concentrations for other components present in this chemical equilibrium, which is your PCl3 equilibrium, which is 0.09 plus X, the 0.09 plus 3.5 times 10 minus 3 molar. So you will get the value to be 0.0935 molar. Okay, since Cl2 also have the same equilibrium concentration in the terms of X, so you can just simply write down. And since it asks for equilibrium concentration for all the components present, so you also need to write everything again, okay, to get the final marks. Okay, so we are done with this one. Okay, so to test your understanding, I will give you the second quiz for this week, which you are given this chemical equilibrium, okay, with the initial number of mole, and you have to predict what is the directions of the equilibrium, either the system is already in equilibrium or not, and if it's not, then you have to predict and state in which direction does the reaction will proceed, and from there you have to calculate the new concentrations or equilibrium concentration for NO gas. Right, so that's all for this video. I'm going to see you guys again in the next video, and please make sure you complete the quiz exercise, and again going to submit in the Google Classroom in the same file, okay, together with your quiz 1 and for quiz 3 coming soon. Thank you for watching. Bye bye.